I hope you have understood the idea of vector space, all right. And what is the linear span? Linear span means you want to create a plane which has all those vectors and the 0 vector, all right. Now, let us go back to the system of equations. What exactly we did in the system of equation? We have the system of equation as Ax is equal to b. What we had was, there was a solution. This solution may be unique, may not be unique, all right. There could be a lot of solutions. Then, or so fix A and B. Then we had this, that there was a solution, or there was no solution, all right. And then we had another system, what was called Ax is equal to 0, homogeneous system corresponding to that, homogeneous system. And here also we had two parts. One was, what was one part? That has a trivial solution and has a non-trivial solution. So, we had these ideas with us. Not only that, if you remember that if when A was a square matrix, then having a trivial solution was equivalent to saying that there was a solution for every choice of B, all right. So, all those notions were there and we tried to understand them. Now, we would like to understand those ideas using vectors, all right. So, this idea that there was a solution or there is a solution for B, this goes to the idea of saying that, idea says that B is a linear combination, of columns of A, all right. There is no solution means for B means that B is not a linear combination of columns of A. Is that okay? So, let us take an example to understand it. So, here I am taking the example as say 1 1 1 1 2 3. Suppose that this is my A, fine. I take B as, so take B as 2 3 4. Then we are saying that 2 3 4 is 1 times 1 1 1 plus 2 times, sorry, 1 times itself 1 2 4 1 2 3, because 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. So, we are saying that this 2 3 4, so 2 3 4 is a linear combination of 1 1 1 and 1 2 3, fine. I could also take say 4 times the vector 1 1 1 plus 6 times 1 2 3, which gives me 6 plus 4 is 10, 4 plus 6 12 4 16 16 and 18 plus 4 is 22. So, again this vector is a linear combination of these two vectors. Is that okay? This is important. We are trying to say that there is a solution for a given B, there is a solution. So, for a given B, there is a solution corresponds to saying that B is a linear combination of things, all right. So, B is a linear combination of columns of A, that is important. B is a columns, 1 1 1 is a column, 1, 2, 3 is another column. So, you can see that they are linear combination of columns, and this is what you say. How do you get this part? You get this part using this vector 1, 1, because multiplying on the right corresponds to saying that you are looking at 1 times this, 1 times this. Is that okay? This one corresponds to 4 times this and 6 times this. Is that okay? So, when I say that B is a linear combination, it means that I am able to solve. So, B is a linear combination. In short, LC, linear combination, means that the system Ax is equal to B has a solution. This is important. Linear combination means there is a solution. Is that okay? When I say that there is no solution, now let us look at this idea. There is no solution means that, for example, if I look at this vector B is equal to 2, 3, 5, then you can show that, there exists no x and y such that Ax is equal to 2, 3, 5. All right, you can show that. How do I show that? Let us compute the RREF of this matrix, augmented matrix. So, the RREF of this augmented matrix will be 1, 1, 1, 1, 2, 3, 2, 3, 5, which gives me nothing but 1, 1, 2, 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 1 is 2, 3 minus 2 is 1, 1 minus 1 is 0, 3 minus 1 is 2, and 5 minus 2 is 3. So, this again if I proceed, I get here 1, 1, 2, 0, 1, 1, 0, 0, 1. All right. So, you can see that there is a pivot here, fine. So, these two are also pivots, but what we are able to see here is that rank of augmented matrix is greater than rank of the coefficient matrix, and therefore, the system has no solution. Is that okay? This you could have also understood from the previous example also. In the previous class, what we had done was, if you look at the previous class, what we had done, that we had this condition that we had these vectors 1, 1, 1 and 1, 2, 3. The condition for the linear span was x minus 2y plus z is 0. All right. So, x plus 2y. So, here x is 2, 3 and 5. So, what we see here is that 2x minus 2y plus z is 2 minus 2 times 3 plus z is 5, which is 7 minus 6, which is 1, not equal to 0. Fine. So, therefore, 2, 3, 5 does not belong to the linear span. So, this also tells me that 2, 3, 5 does not belong to the linear span of the vectors 1, 1, 1 and 1, 2, 3. Fine. Here this tells me that this vector 10, 16, 22 or 2, 3, 4, they belong to the linear span of 1, 1, 1 and 1, 2, 3. Fine. So, whatever we had studied in the previous class about linear span, we are just trying to check now whether a certain vectors belongs to that linear span or not. Is that okay? So, when I am solving the system Ax is equal to B, there we are looking at intersection of planes, intersection of lines and so on. Here we are saying that whether a vector B belongs to column space or not. So, we are talking of whether B belongs to linear span of columns of A or not. Is that okay? So, the things have changed. There we are looking at whether a system has a solution or not. Fine. The language there gets changed to whether B belongs to the linear span or not. So, whether some vector is in the subspace or not. Fine. So, that is one important idea. I would like you to keep track of this. We will be using it again and again. The next idea that I said was looking at trivial solution and a non-trivial solution. So, let us look at example to understand what means trivial solution. So, look at these two itself. We have the two vectors 1, 1, 1, 2 and 1, 3. I want to look at the system Ax is equal to 0. So, I want to solve 1 1 1 2 1 3. Does there exist x y such that this is equal to 0 0 0, all right. So, when I solve it, what I see is that x is equal to 0 is equal to y is the only solution, all right. So, what we had said is that this system has only the trivial, has only the trivial solution. Is that okay? Fine, that is important for us. What we are trying to say is that I have a set of vectors, again I am looking at columns. I am asking that whether the corresponding homogeneous system has only the trivial solution or has a non-trivial solution. Fine. So, here we see that this has only the trivial solution, and since it has only the trivial solution, we say that these two vectors 1 1 1 and 1 2 3, these are linearly independent. All right. So, why you are saying they are linearly independent vectors? Because this system has only the trivial solution. Is that okay? That is very important for us. Be careful when you are saying that something is linearly independent, it means the solution is only the trivial solution. Another set of examples. For example, again in R3 itself, suppose I look at 1 1 1, 1 1 1, 1 2 3 and 2 3 5. Fine. Look at these three vectors for us. So, I should have written it with some gap here. So, I have got these three vectors, all right. So, I make a set out of it. So, we say that this set, this is linearly independent or not, that is the question. Fine. So, what we do when we say that this system, these three vectors is linearly independent or not, we solve a system A x is equal to 0. Now, what is the size of the matrix A? This matrix A has size 3, 1 1 1, 1 2 3, 2 3 5. There are different ways of doing it. We will learn that if determinant of this is not 0, then we will get that this is linearly independent. Fine. Or you can look at the RREF. We have already computed the RREF of this matrix 1 1 2, 1 2 3, 1 3 5. What we see is that the RREF of this matrix is identity. So, RREF of A is identity, and therefore, what we know is that the system A x is equal to 0 has only the trivial solution, all right. It does not have anything else, it does not have a non-trivial solution, it has only the trivial solution because RREF of A is I3, and therefore, this set of vectors is linearly independent. Is that okay? So, it turns out that these three vectors are linearly independent. You have already done the calculations here, and we will look at them again and again. Fine. And when the system A x is equal to 0 has a non-trivial solution, then the columns of A are said to be linearly dependent. Fine. So, there it was independence, here it is dependent. Is that okay? So, there are four ideas that we had when we solve the system A x is equal to b, whether it had a solution or not, that gave us the idea of solution. There is a solution means linear combination is there, or the vector b belongs to the linear span. If there was no solution, it means that there is no linear combination, or the b does not belong to the linear span. Fine, those ideas were there. Then we go to the homogeneous system and look at the idea that A x is equal to 0. If it has only the trivial solution, only stressing on it, it means that the only solution is 0 0 0 0 0. Then we get independence. If it is a non-trivial solution, it means we are looking at the set of vectors or the set of columns that I am looking at, that is linearly dependent. Fine. So, let me write the actual definitions now. I have given you examples to make you understand. So, definition. So, let V be a vector space and S is equal to U1, U2, UK be a subset of V. And V is a vector space. I am not writing over what? Over F. I have to say that, it is very important, over V, fine, over F, fine. Then B is said to be a linear combination of elements of S or B is a linear combination of vectors U1, U2, UK if there exists alpha 1, alpha 2, alpha k belonging to F such that B is equal to alpha 1 U1 plus alpha 2 U2 plus alpha k UK, fine. So, linear combination means I have this idea with me, or what I am saying is, look at the system U1, U2, UK, fine. I have this alpha 1, alpha 2, alpha k and this is B I have. So, this is the vector of unknowns, or I have this as variables and I am solving the system A x is equal to B for me. Is that okay? Fine. So, if able to solve this system, if there is a solution, then we say it is linear combination, otherwise it is not a linear combination. So, it is important for you to see that I am writing a matrix coming from U1, U2, UK. U1, U2, UK need not be an element of Rn, it could be any, whether it is polynomials or anywhere that you are looking at some set of vectors, I can write them in terms of a matrix. So, here my columns are those vectors. Is that okay? How they look like is immaterial, they could be functions, they could be polynomials, but I am writing it in that form, fine. 2. S is said to be linearly independent subset of V over F. I am stressing on it over F if the system U1, U2, UK alpha 1 to alpha k is equal to 0 in the unknowns alpha 1, alpha 2, alpha k belonging to F has only the trivial solution. Fine. So, it is said to be linearly independent, fine, if it has only the trivial solution, fine. Dependent if it has a non-trivial solution. So, dependence means non-trivial solution and independence means only the trivial solution, only is very, very important, only the trivial solution. Is that okay? So, you have to be careful when you do things, you have to understand them. So, let us take some examples to have a clarity on these ideas. Linear span you have already understood, linear combination I hope you have understood by examples. Let us look at linear independence dependence so that we proceed further, all right. So, examples, I am not going to linear combination, only linear independence dependence, all right. Suppose I have this S consists of just the 0 vector, fine. what can I say about S? S equal to 0 is what? Is a linear independent oblique dependent set. That is the question. All right. So, again let us go back. The idea was that I have to form a system of equation. I have to form a system of equation in which the matrix A was nothing but the vector that was given to me. Let us go back here. That I have to form a system with A as vectors coming into it. So, I have the vector A here, unknown for me is x, and I am solving it here. Is that okay? So, I need to solve where x is unknown. Fine. What we see here is that x is equal to 1 is a non-trivial solution, and this implies this is a linearly dependent. Is that okay? Example 2, S is equal to, say, let me write in terms of 0 0 and say 1 2. Fine. What about this? Again form the vector 0 0 1 2. You can see here the solution is 1 comma 0 is a solution to give me 0 0. So, this is a non-trivial solution, implies S is linearly dependent. Fine. So, you are always solving a system here A x is equal to 0. This is what you are doing. This is your x, this is your A, and this was your 0. So, we see that again the matrix multiplication is here to help 1 times 0, 0 times this gives me this. So, what we can see from here is that any linearly independent set, as a remark you can see here 0 vector cannot belong to any linearly independent set. Fine. This cannot belong to any linearly independent set. As soon as you have a 0 vector in a set, that set becomes linearly dependent. Fine. Let us look at third example. I take S as just a single vector 1 2. What happens? Now, I again look at 1 2, this vector times this should be 0 0, x is unknown, and this will imply that x equal to 0 is the only solution. So, it is the only solution means 0 0 is the only solution. So, this is only the trivial solution only. Fine. This implies S is linearly independent. So, a singleton non-zero vector. So, what you are saying here is that a singleton non-zero vector is linearly independent. Fine. Some more examples. Fourth, now we would like to look at the role of scalars being playing the role. So, let us look at C2 as a vector space over R, and 5 C2 as a vector space over C. So, over C means scalars are complex numbers here, scalars are complex numbers, here scalars are only real numbers. Fine. So, let us look at two sets here, same set of vectors in the two. So, I would like to look at the vector here 1, 2 and I, 2i. These two are subset of C2. Here also I have the same thing 1, 2 and I and 2i. Fine. C2 is a vector space. Here it is over real numbers, here it is over complex numbers. So, in the first case here I want to look at, so make this matrix 1, 2, I and 2i. Let us look at xy is equal to 0, 0. Want x and y belonging to R. That is important because scalars are real numbers. So, therefore, I am only allowed to take x, y belonging to R. Fine. So, therefore, if you would like to solve here, this implies that x plus I times y should be 0, x and y real implies x is 0 and y is 0. Fine. Similarly, for the second equation you can see here that x has to be 0, y has to be 0, all right. So, therefore, we only have the trivial solution. So, only the trivial solution. Is that okay? So, therefore, this is linearly independent over R. Fine. But let us look at here in this example now, all right. In this example, you have 1, 2, I and 2i. I have to look at xy equal to 0, 0, but x and y are now complex numbers. Fine. Since they are complex number, we can see that take y to be equal to minus I and x to be equal to, or let me take x to be minus I and y to be 1. Then what I see here is that we get 1 I 2, 2i times minus I 1, which is minus I plus I minus 2i plus 2i, which is 0, 0, all right. So, therefore, this is a non-trivial solution, all right. So, therefore, this is a linearly dependent over C. Fine. So, this is how the scalars make a difference, where you are looking at, all right. So, both of them are subsets of a C2. C2 is a vector space, but one is over real numbers, the other is over complex numbers. So, the definitions of linear dependence do depend on set of scalars, all right. This is what you have to be careful about. I would like you to understand them. Fine. Fifth, some more examples here for me. Fifth, let us consider these, all right. So, these are set of continuous functions. So, you can prove that V is equal to set of continuous functions with a domain say minus pi to pi, that is the domain, all right. So, sum of two continuous function is a continuous function. Fine. If you multiply a scalar to a continuous function, it still remains a continuous function. So, you can prove that set of continuous functions with domain, whatever domain you take, is a vector space. So, V is a vector space over R. We are allowing the scalars to be real numbers. Now, in this set I would like to take vectors, say S is equal to 1 sin x and cos x. These are three continuous functions. I want to check whether they are linearly independent or not. Fine. So, if I want to check whether they are linearly independent or not, I have 1 here, sin x here, cos x here. There are three vectors, so I will have three unknowns x, y, no, so x, y, z is a problem. So, maybe alpha 1, alpha 2, alpha 3 is equal to 0. So, I want to solve this system. solve this system for all x belonging to the domain minus pi to pi. Fine. What we are saying is the left hand side is a continuous function for whatever alpha 1, alpha 2, alpha 3 you choose. They only need to be real numbers, that is all you are saying. And the right hand side is a 0 function, 0 continuous function. So, you are saying that two continuous function, the 0 function is one side, the other side it is alpha 1 plus alpha 2 sin x plus alpha 3 cos x have to be 0. Fine. What is the solution for this? I would like you to see that this thing leads to looking at following: alpha 1 plus alpha 2 sin x plus alpha 3 cos x is equal to 0. Fine. Now, this is valid for all x belonging to minus pi to pi. So, there are different things we can do. It turns out that more than continuous, it is also differentiable. So, I can differentiate both the sides. So, if I differentiate both the sides, I can look at here alpha 2 cos x minus alpha 3 sin x is 0. I can again differentiate it to get minus alpha 3 sin x, alpha 2 sin x minus alpha 3 cos x is 0. I can use this equation and this equation now, just add of them to get that this will imply that alpha 1 is 0. Fine. Now, I can use these two to show that this will imply alpha 2 is 0 and alpha 3 is 0. Fine. So, once I put this, note that the equation is sin x cos x minus sin x times alpha 2 alpha 3 is equal to 0 0. This is an invertible matrix, minus sin s square x minus cos s square x is minus 1. So, therefore, the only solution is a trivial solution. Fine. This determinant is minus 1, implies invertible, implies unique solution 0 0. Fine. So, therefore, what we are saying is the set 1 sin x cos x is linearly independent. So, even though we had only one equation here, we have been able to generate 3 equations by differentiating, all right, because they are differentiable functions. We could have also done one thing, that since this is valid for every x, I can evaluate this at different points. So, I can evaluate at x is equal to 0, x is equal to pi by 2 and x is equal to say pi. So, if I do x is equal to 0, what do I get? Alpha 1 sin 0 is 0, alpha 1 plus alpha 3 is 0. At x is equal to pi by 2, I will get alpha 1, sin of pi by 2 is 1 and cos of pi by 2 is 0. So, I will get this, and at x is equal to pi, I will get the third equation, which is alpha 1 sin of pi is 0, cos of pi is minus 1. So, minus alpha 3 is 0. So, I can solve this equation and prove that alpha 1 is equal to alpha 2 is equal to alpha 3, 0 is the only solution. Fine. So, you can proceed in whatever way you want and try to prove things like that. Is that okay? Fine. As the last part, I would just like to prove this theorem, or just let me state some things first. So, remark. What we saw was that, recall it, 0 vector cannot belong to any linearly independent set. We saw this. Fine. Second remark, let S be a linearly independent subset of V over F, then any subset T of S is also linearly independent. Fine. So, T is a subset of, that is important, T is a subset of S. S is linearly independent, this is bigger one is independent, then the smaller is also independent, fine. So, when I am talking of independence dependence, we are assuming that our sets are non-empty sets, fine. Otherwise, viciously we will say what happens to the empty set. Third one, let S be a linearly dependent set, dependent set in V, then any superset, fine. So, I have got T, T contains S, all right. This is linearly dependent, T is a superset, any superset T of S is also linearly. Is that okay? So, you can prove it yourself, fine, because idea here is, if you look at the idea here, so let us look at the idea here. I have S which is U1, U2, UK. Suppose T is say U1, U2, UL, and L is less than or equal to K. There are some collections. This is linear dependent will imply that this sector U1 to UL times alpha 1, alpha 2, alpha L equal to 0 has a non-trivial solution, fine. Is that okay? So, you have a non-trivial solution here, linear dependence will imply that. So, if I want to look at here, I have the same thing here U1, U2, UL, UL plus 1 till UK. Again I can patch up here with alpha 1 to alpha L and then zeros here, fine. So, if I look at this has a solution which is non-trivial will imply that this will also have a non-trivial solution, because alpha 1 to alpha L are the same, U1 to UL are the same, fine. So, this will also be there. So, this will also have a non-trivial solution, and therefore, there will be a contradiction, fine. I would like you to try the similar thing for 3. So, I would like you to understand these things which are very, very important, fine. In the next class, we will look at some more examples of linear independence dependence, all right, to do with matrices, and then look at the theorems to understand these ideas, because linear independence dependence will result into again solving system of equations and the ideas which were related with what are called the RREF of matrix. Recall that we assumed that RREF of a matrix is unique, we did not prove it, we did not do anything there. So, those ideas will be coming into play for us. We also had the idea that we have the definition of row rank of a matrix, but we did not talk of column rank. So, we would like to look at row and columns at one go. It will take some more time for us, but all those ideas will get related with what are called independence. So, when I say that rank of a matrix is K or rank of a matrix is 3, it means that that matrix has exactly 3 linearly independent rows or exactly 3 linearly independent columns. We will get into all those things in the next class. Thank you.